Okay, we now consider the case with inequality constraints. So recall that the problem is given by the follows. We're trying to minimize fx such that the hx is equal to 0, gx is less than or equal to 0. Okay, so this is our typical setup for constraint optimization problem. And here, this constraint is the equality constraint. This is the inequality constraint. Both of them are vector valued. So here it has n components, m components, right here. So it has h1 through hm, and this one has p components, which is from g1 to gp. Okay, as we indicated here. All right, and these two constraints will give rise to this convex set omega. So all the points that are satisfy these two constraints form this convex set omega. Actually, for convex optimization, the omega is convex, and in this case, typical setup is that the g is a convex function. The g is convex function. So this one here defines the sublevel set of the function g at c equals to 0. Call that we define sublevel set of g to be the set of points where the gx is less than or equal to 0. Okay, let's say that is 0. So this is a convex set. If g is convex, then this is a convex set. And you take the intersection of this set. Just remove this. Take the intersection of this and this set, where this hx is equal to 0. So for convex optimization problems, the hx is often said to be a affine function, which means that it is written as that. A is a matrix, B is a vector, so ax minus b equals to 0. This gives basically gives you a hyperplane, and you take the intersection of the hyperplane and this sublevel set, which is a convex set, and take the intersection of two convex sets. This is a convex, and the hyperplane is definitely convex, right? You take the intersection of the two, and that set you end up with is called the omega. So in convex optimization problems, the h is a affine function. Gx is a convex function. Okay, and then it's guaranteed that this omega is a convex set. We didn't specify the h to be a convex set earlier in this chapter. The reason is hx equals to 0, h itself doesn't have to be, an affine function for this to be a convex set. It just has the typical setting is that it's an affine function. The reason why this is true is you can imagine this situation. Say I have a function that is pretty weird, but it's just that it takes value 0. Oh. It takes the value 0 here, and then it can go like this. So it doesn't matter what happens. So this is my h function. This is my hx. So it doesn't matter what happens outside this area, as long as that the points where this function touch 0 or is equal to 0 is a convex set. Then we don't need to worry about anything else because hx equals to 0 restricts yourself to this part, which is convex. Okay, so the hx itself doesn't have to be a affine function or even doesn't have to be a convex function. But what we really need is where this function is 0. So, but for x to be 0, then this part we can think it as a intersection of a convex set and affine function. Convex set and a hyperplane. Okay, so that's why we said that in practice, the convex optimization problems are formed by the intersection of these two sets. So the constraint g is convex, and this h is convex, and of course the f is convex function. And all this, if we have this set up, then this part, this problem is called convex optimization problem. All right. Okay, so when you see a problem or convex optimization problem, you probably want to assume that this is alpha, and this is convex, and this is also convex. Okay, so now get back to this theorem. So what we're trying to do in this theorem is to show that the Kkd condition is a sufficient and a necessary condition for a point to be a global minimizer of this optimization problem. Okay, and the setup is as follows. We have a function f, which is objective function. It is C1, meaning that it's continuously differentiable and is convex. And this omega specified by this 2, which is also convex. It's convex. I should add this as before. It's a convex set where this H is a mapping in this way, where it has m components, and G is a function in this way, and it has p components, and they're both A1. You just make sure that they can give rise to a convex set omega here. Then the conclusion is that x star is a x star in omega is a global minimizer of f over omega if and only if there exists the Kkd multipliers, or this is the Lagrange multiplier, this is the Kkd multiplier, such that this lambda star, this mu star is greater than or equal to 0. Remember that this is the multiplier for the h. This mu star is the multiplier for the gx. There exist these two multipliers such that the first one is the derivative of, or the gradient of, the Lagrange function with respect to the variable x, right? I still recall that. So it's just that we have this Lagrange function, which is a function of x, lambda, and mu, and it's written as the f of x plus the lambda times hx plus mu times gx. Okay, and then we take the gradient with respect to x. We will end up take a gradient of this with respect to x. We will end up with this one. Okay, so that's the first condition, and then we also know that the other conditions include the hx must be equal to 0, gx must be less than or equal to 0, and this is true because x star must be a feasible point, and also the mu star has to be greater than or equal to 0. That is a requirement for this Kkd variable, Kkd multiplier, and finally the inner product of the g and mu is equal to 0. This is called a complementary slackness condition, and this ensures that when we look at the mu I, because this is equal to the sum of mu I star, which is the ith component of the vector mu star, and this gi x star, which is the ith component of the gi vector, okay? Because the g of x star is a p-dimensional vector, so the gi is just the ith component from 1 to p. So this is equal to 0, and we know that this is greater than 0. Sorry, this is first one is less than. This one is greater than or equal to 0. This one is less than or equal to 0, and this equal to 0 means that for each term, at least one of these two. So that for these p terms, at least one of these two is 0. Right? So for the p for each of these p terms, we have for each of the p terms we have this, and at least one of them is 0. Otherwise, the product of this will be negative, and other ones will be non-positive, and take the sum, it cannot be equal to 0. Okay, so if you want it to be 0, then every term of this must be equal to 0. That means at least one of these two terms is 0. So that's what we discussed in the Kkd condition. And we know that what we're trying to do here is to prove that this Kkd condition is also sufficient. So it's necessary is something we have proved before. So, and that is this direction. If x star is a global minimizer, then it has to satisfy the Kkd condition, and it has to be a Kkd point. So that's why this is true. So So this direction is no problem. And then here, what we're trying to do is to show the other direction. Suppose the Kkd condition holds. Can we show that the point x star is a global minimizer? Okay. Suppose the Kkd condition holds. In other words, suppose the x star satisfies the following property, that there exists some lambda star and a non-negative vector mu star such that this holds, and x star is in the feasible set here, then can we claim that x star is a global minimizer? Okay, so this is what we're trying to do here. Okay, to prove this, let's first recall that the function f is a convex function. So that means for any x in the set omega, this inequality holds. Right? This is what we have been doing several times so far. So because of this, we know that since the gradient f can be written, gradient f added by these two numbers is equal to the 0 vector. So that means gradient f is equal to negative of this. Okay, so I just substitute the gradient f by the negative of this back in here. Okay, so I'm just put this back in here, and now I will get that. Right, just simply substitute that gradient f star. All right, so now with this, we can see that for any x, since x star, for any x in the domain, since x star plus this alpha times this one is a point in omega as well. So this is because that we have this omega, for example, is convex set. We have this x star, and there's some x. Now, this is the x minus x star. This vector is x minus x star. Okay, so x star plus alpha times x minus x star, where for alpha between 0 and 1 is some point in between. So this point right here is x alpha. Right? This point here is x alpha, which is equal to x star plus 1 minus alpha. Sorry, just alpha times x minus x star. Okay, and this this point is apparently also in omega, because any point connecting 2 points in omega will be also in omega since omega is convex. All right, now we can see that because this point is in omega, so this x alpha needs to satisfy both of the conditions in omega. So that means h of x alpha must be equal to 0, and g of x alpha must be less than or equal to 0. Right? That's what we must know. Okay, we know this. And for the first one, it's similar as before. Since we know that the h of x alpha is equal to 0, so we subtract this by h x star, which is also 0, since x star is a feasible point as well, and then divide by alpha, then we get this quantity, and then we know that this is always 0, no matter what alpha is. Okay, so the alpha shifts from 0 to 1, but for any alpha, we know that this is equal to 0, so we take this fraction, or take this ratio, we know this is always 0. So when we take the limit for alpha going to 0, it's still 0, right? Because this is true for any, this is equal to 0 for any alpha. So when we take the limit for alpha going to 0, this is still equal to 0. But now realize that, need to realize the same thing as before, realizing that this is like you take a function psi of alpha that is defined as h of x star plus alpha x minus x star. It's like you're taking the derivative of psi with respect to alpha and set alpha to 0, right? That's exactly what this limit is. So the psi prime at 0 is just the limit as alpha goes to 0, and psi alpha minus psi 0 divided by alpha. Okay, and that's the limit is exactly this limit right here. And we know that this must be equal to 0 since this quantity is 0 for any alpha. All right, and that implies that this is equal to 0. Well, when this is equal to 0, we know that this is just gone. Okay, it will be gone. And then we'll end up with the f of x greater than or equal to f of x star minus this. Okay, now this term is a little bit troublesome. Let's see how to handle that term. So similar as before, we know that since this point, which is the point that we just draw, is in the middle point between x star and x, it is also a feasible point. That means it's also in omega. Since it's in omega, we know g of this point must be less than or equal to 0. That's a requirement for omega, for the points in omega. So now we know this is less than or equal to 0. And because mu star is greater than or equal to 0, it's the non-negative vector. So when we multiply these two together, we know that this is less than or equal to 0. Okay, so you have a non-positive vector here, and you have a non-negative vector here. So when you multiply them together, the inner product will be giving us a number less than or equal to 0. And then because of that, we can see the numerator right here. This is the quantity, as we said, this is the quantity that's less than or equal to 0 for any alpha, right? And at the same time, this is equal to 0. This is a complementary slackness, right? This is equal to 0. So you have something less than or equal to 0 minus 0 divided by alpha, which is positive, which is non-negative, right? Alpha is greater than 0. Alpha is between 0 and 1. So we know that this whole thing should be less than or equal to 0. And this thing, as similar as before, is just just this. It's just this. And again, the situation is because we set psi of alpha to be the mu star transpose times g of x star plus alpha x minus x star. Right? We can do that. This gives us a number. So it maps alpha to a scalar, which is inner product of these two. And then we know that this term is nothing but just a psi alpha minus psi 0 divided by alpha. And then we know that this is less than or equal to 0. This is equal to 0. So when you divide by alpha, this whole thing is less than or equal to 0 for any alpha between 0 and 1. Then when we push alpha to 0, this whole thing will be less than or equal to 0. And that means the psi prime at 0 should be less than or equal to 0. But the psi prime at alpha, we take the derivative with respect to alpha, we're going to use the chain rule, right? We're going to use the chain rule. The alpha is only in G, so I keep the mu star transpose and then take the Jacobian with respect to Jacobian of G and evaluate x star plus alpha x minus x star. And then I will need to take the derivative of alpha of the inside, which is x minus x star. So I will have x minus x star. All right, and then we know that from here we know that the psi of 0, psi prime of 0 will be just setting the 0 alpha to 0 of the above. So I have this, so minus x star, and that's why this must be less than or equal to 0 as we showed here. Okay, it's less than or equal to 0, and that is exactly this term, which is less than or equal to 0. So now if this term is less than or equal to 0, I know that here this term is gone, as we just showed, it's totally gone. This is not less than or equal to 0 means that this whole thing will be greater than or equal to 0. So I know that the right hand side is f of x star plus something non-negative, and it must be greater than or equal to f of x star. Okay, and now what we showed is that for any x in omega, f of x is greater than or equal to f of x star, and that means x star is a global minimizer. Okay, so that completes the proof. Okay, this completes the proof. Okay, so let's look at an example. Suppose we have, so we're trying to use the Kkd condition to see that it is, if we have a convex problem, then the Kkd condition is a sufficient condition for optimality, global optimality. Okay, and let's see the problem here. Suppose we can deposit this xi amount of money into a bank account. So starting point is that we don't have any money in the bank, and the xi will be the amount of money that we deposited at the beginning of the ith month for I equals 1 through n. So we can do that for n months. the monthly interest is R. So that means at the end of each month, we can get 1 plus R times the available money, the money available at the beginning of the month. Then now we have a total number or total amount of money, which is called D, to deposit. But we can decide how much we deposit in each month. And the question is exactly the same as we were trying to do to maximize the total balance, including the interest at the end of the month. So suppose we have this money to deposit. Should we deposit it, distribute this money to different months and then collect the money and collect the deposit and the interest at the end of the month? And or how should we deposit or distribute this money to deposit? And apparently, you know that we should always, if there's no other condition, we should always just deposit all the money into the account at the first month, at the beginning of the first month, so that the interest can always accumulate. Right? That would be that would be the only way to maximize the total balance. And what we're trying to do here is to use the Kkd condition to verify that. Apparently, this is a kind of simple question or very trivial question, but the goal here is to show that these indeed can be implied by the Kkd condition. Okay, so the setup is like that. We have we try to deposit the xi into the account, and the total number of the total amount of money we can deposit is equal to D. So here the x is written as a vector of x1, x2 up to xn, right? These are the money we should deposit. And the E is this vector. So 1, 1, all the components are 1. So when we take the inner product of x and E, we just take the sum of the components of x. Right? And we know that this should be equal to D because that's the total number, the total amount we can deposit. And then the x greater than or equal to 0, apparently, we cannot take out money from the bank. We can only deposit. And what we're trying to maximize is that if we set up this, if I deposit x1 in the first month, then this part will always accumulate interest starting from the first month, right? And then when I deposit this into the second at the beginning of the second month, then this will accumulate interest starting from the second month, right? So on and so forth up to this one, they will be start to accumulate. It will accumulate the interest only for the last month, right? So the total number, total amount of money we'll get will be 1 plus r times the first x1, and you can do this to 1 plus r to the power n because it will accumulate interest for n months if we deposit x1 in the first month, at the beginning of the first month. Similarly, x2 will be multiplied to x1 plus n, 1 plus r to the power n minus 1, since it can only accumulate interest for n minus 1 month. Okay? Similarly, up to the last one, it can only accumulate interest for 1 month. Okay? And what we're trying to maximize is the inner product of this x and this vector, which is 1 plus r to the power n, 1 plus r to the power n minus 1, all the way to 1 plus r to the power 1, which is 1 plus r itself. Well, we're trying to maximize the inner product of this vector and this vector. It's the same as minimizing the inner product of this vector times negative of this vector, right? So that's why we set the C to be the negative of that. So the C is negative of this vector. So we're trying to minimize the inner product of C and X, subject to the constraint here. Okay. So the setup is pretty clear, right? And this is apparently a convex optimization problem. This is actually a linear program problem. Okay. This is actually a linear program. Okay, so instead of trying to solve it, let's see that if our intuition at the beginning is correct, if we should deposit all the money in the first month, at the beginning of the first month. And to do that, we just need to check if I choose my x star to be d 0 0. So that means I set x1 to d and all the other values to be 0. Then apparently this satisfies the constraint, right? Satisfies the constraint here. And let's see what are the lambda and mu star should be. Now let's set lambda to be a 1 plus r to the power n. Lambda star. Okay, let's set this lambda star to be that, and the mu star to be this. And do not ask me why we get this. Actually, if we can solve the Kkd, we can actually obtain this. But let's say that at this moment, we figure out these two multipliers such that just to make sure that it's hold. Okay, and actually, one way to do that is to set the x star to be the one we just had. So the x star is equal to d0 0. And now let's try to figure out if the lambda star and the mu star satisfy that. And apparently, if we do that x star, write down all the Kkd conditions we need. The Kkd condition is that we start from the Kkd function or the Lagrange function of x, lambda, mu, and this is supposed to be the objective function, which is 3 transpose x, plus lambda times the linear equality constraints, which is E transpose x minus D. Okay, E is a vector, D is a scalar, plus mu times the gx. But gx right here, right, the gx, according to this, my gx should be set to negative x. So that gx less than or equal to 0 implies it's equivalent to x being greater than or equal to 0. So this is my gx, which will be negative x. So I need to take an inner product of that. And then, to get the Kkd conditions, we need to take the gradient with respect to x for this Lagrange function. And that gives me x, so SC. So you can see when we take the gradient with respect to x, I will get C plus lambda times E plus or minus mu. Okay, that is the first condition that we have here. And then we listed the constraints for x, which is the equality constraint, inequality constraint. And then for the lambda star, mu star is always negative. And then finally the complementary slackness. This is the mu star times x star, or the mu star times g star. G of x star must be equal to 0, but g star is equal to negative x. So that's equivalent to that. Okay, so this is the Kkd conditions. And say my x star is that, my lambda star is this, and my mu star is this. Let's see if they satisfy that. Okay, actually it's pretty easy to check. And apparently when I have this let's see. Okay, first of all, these two can be easily checked, right? Because the x star is a feasible point. So these two are okay. Mu star is said to be that, said to be this. And well, because C is that vector we showed earlier, C is this negative 1 plus r to the power n, 1 plus r to the power n minus 1, all the way to 1 plus minus 1 plus r. Okay, so the C plus lambda star E will be this C vector here, plus lambda star was chosen to be that. So, and what E is E here is or E here is just 1, so that means I'm going to add up 1 plus r to the power n for each term, because this is the same constant multiplied to each term, and each term is 1. So that's why I end up with that. And apparently, the first components add up to 0. Second components that add up to like 1 plus r n minus 1 plus r n minus 1. And all the way to the last one, which is just 1 plus r to the power n minus 1 plus r. Okay, so only the first component is 0, the others are non-zero. Now we only need that because if this is a lambda c plus lambda star e, that's what this one is. Okay, and my mu star, if I set this mean plus my mu star must be equal to that. Okay, my mu star is equal to that. So this one is verified. So this one is verified. This one is verified. This one is verified. This is also verified. And only the last one, if the inner product of these two is equal to 0. Well, what I know about this two is that the mu star, which is this or this, has 0 on as the first component, the non-zero as the remaining ones. But my x star is d at the first component, the 0 for the other component. So when we take the inner product of these two are apparently to be perpendicular. So the inner product of these two is equal to 0. Well, so far we showed that all of these conditions are satisfied if we set x star to be that and the lambda star and mu star to be this. And that means the x star is indeed a Kkd point. It satisfies the Kkd condition. And according to our theorem above, since it's a convex problem, and this x star must be a global minimizer. And that is indeed what we were, our intuition at the beginning. We should just deposit all the money into in the first month, beginning of the first month, and this Kkd condition just verifies that. Okay, now we start the last chapter about the algorithms for constraint optimization. So we are trying to develop an actual algorithm to solve constraint optimization problems. The first one, we should start the first one by modifying some algorithm that we have been familiar with. Previously, we know that when we try to solve an unconstrained minimization problem, which is that minimizing this fx, where we don't have any constraint, the x is just in Rn, then we know that a typical method for doing that is to do this gradient descent, okay, or the descent method. So a typical one is that we set this to be alpha k dk, okay, and the typical choice for the dk is negative gradient gradient f at xk. So this just set dk to be negative of the gradient. Okay, so this is called gradient descent. But generally, we can set the descent direction to be something more smarter. For example, we can do the Newton's or quasi-Newton's method, or can do conjugate gradient. Those methods are typically faster than the gradient descent. But this is a general procedure, right? We do this descent method in that way. We just need to figure out what are the alpha k, what are the dk. Okay, and this dk is called the descent direction, and this alpha k is called the step size. Okay, and that's typical for an unconstrained minimization problem, but it cannot be directly applied to constrained optimization problems. Since when we do this, we basically we know that this is our set. Then, for example, this is where the xk is, and suppose that we the dk is pointing to that direction. So I know that when my step size is small enough, we may still end up with some point inside the omega. But if I take this alpha k slightly larger, then it could be outside. Okay, or for example, my xk is here, and then I chose my dk to be that direction. Then no matter how far I go, I always immediately will be land outside of the omega, right? So that's why the gradient method, just like that, doesn't work. the new point we get may not be a feasible point, may not be in the feasible set. And a very intuitive way of correcting this is to do this projection. So every time we finish this step, we got the xk plus 1, then we just need to project it back to the set omega. Okay, and this method is called the projected gradient method, or the PG. Okay, if you do the gradient descent for this step, for example, if you chose this to be negative gradient, then you do the projection after this gradient descent step, then it's called a projected gradient descent. Okay, but generally, if you just set up this way, then it's called a projected gradient method. Okay, in this case, the key is that how do we do this projection? So the projection is denoted by this capital pi. The question is how do we do this projection back to the set omega? And apparently this one itself may not be easy, because projecting some point back to the set is another optimization problem, right? The reason is if x is already in omega, then that's okay. But if x is outside of omega, how do we find the projection? The projection was defined to be the, say I have this as my omega, which is not necessarily convex, right? And then we'll have this point right here. Well, I could have a point x here, and then projection is pretty simple. It's just look at where the point in omega that is closest to the x, and probably this point right here is closest, right? And if it's here, and then probably it's clear that this would be the point. It's closer to x. But if x is here, then we're probably not very sure. Maybe while it's here is still fine, but maybe my x is here, right? Then in this case, we don't even know if there is only one result, because it could be projected here, could be projected here. They both have the same length. Okay, so that's the issue with the projection. First of all, it may not be easy to compute. The second is that it may not have only one solution. Okay, but still we can define this projection. The projection is said to be the point that is closest, the point in omega that is closest to omega, or in other words, for any given z, say this is z, call this z. For any given z, we want to find the point in omega that is closest to z. So I want to find this x, or maybe this x in omega, such that this one, the distance between them is minimized. All right? So this itself is an optimization problem. And as I said, the argument here tells you the result, and it may not be just giving you one solution. It could give you multiple solutions, or even a set of points. Okay, even a set of points. So that is the issue here. But indeed, in some cases, the projection is easy to find. So at least there's some examples where the projection is pretty easy to find. For example, you're projecting your x to this set. What this set is, so in 2D case, for example, this is the infinite norm of is less than or equal to 1, meaning that the largest component, or the largest magnitude of the components of x is less than or equal to 1. So in 2D case, what that means is just this. So if I have x1, x2, then this is 1, negative 1, 1, negative 1. So that means your x must be in this box. Okay, and projecting some point back into this box is pretty simple. You can imagine that it doesn't matter where the point is. I just need to, project it to this, and usually you can do this by just the so-called clipping. For example, you get the value. You have this z value, which is z1, z2. Then you just look at each component separately. If the z1, for example, if it's outside of the range negative 1 to 1, then just project it back to negative 1 to 1. Right? For example, if z1 is 3, in this case, for example, z1 is 3, you just project to 1. Okay? If it's negative 2, for example, you just project to negative 1. Right? Things like that. Yeah, this is called the. This is pretty easy to do, as you can see. And in general, if we have a rectangle or box like that, we know that the ith component is between this. Then apparently, if it's outside of this range, we just project it back. For example, if xi is less than ai, we just set xi to ai. Or if xi is bigger than bi, we just set it to bi. If xi is in between, then we don't change xi. Okay, and then we do this for each component, and then we project the point back to this box. So this is the very typical one. This is called the box constraint, because this omega is a hyperbox or hypercube in a dimensional space. So it's called a box constraint. Okay, and we can also check, for example, this one. This is typically just the unit ball in Rn. Okay, and to project a point back to this, we just need to see that if z, the norm of z is already less than equal to 1, then we just set the project to the pi of z is just equal to z itself if the z is already in the box, in the ball. And if z is outside of the ball, then what happens is, for example, in 2D case, if z is somewhere here, and then what I can do to project this back to this ball is to just shrink the length of z such that the length is equal to 1, right? So this will be the point for projection. So the pi of z should be just z over the norm of z. Okay, so that's how we do that one. And similarly, to project to this surface, we just need to, right? We just need to set the pi of z to be directly set it to be z over the norm of z. Okay, no matter what z is, except for z equals to 0. But even because when z equals to 0, how do we project? We have this circle to project to. Okay, this is my circle. My projection point must be on the circle. Well, if it's some other point or here, this should be fine, right? So it will be clear just the closest point. You just make a connection between the point and the origin and project it. You take the intersection of the line and this curve. And similarly here, if you have a point in here, then the projection is just to the closest point there. Okay, but if z is just equal to 0, then what we can do? Right? All the points on here have the same equal distance to this origin, and in this is the case that we mentioned earlier. We could have more than one, or could be the projection point could be more than one, or could be even a set of points. And this is exactly the same situation. The origin, projecting origin to the circle, all the points on the circle are projection points. Okay, and we can, so this is the fourth example. And we can also consider this. This is the set of points where the L1 norm is less than equal to 1. So previously we considered L infinity norm less than equal to 1. For L1 equals to less equal to 1, what that means in 2D, that means this diamond is the points, it's a set of points whose L1 norm is equal to 1. So if we do the projection, you can imagine what's going to happen. Right? This one is not that trivial anymore, but I still have a closed form. Okay, if you can look for it, you're interested in. So this is the one example. The last example is pretty common. The omega is described by a hyperspace. Okay, it's a subspace, linear subspace of Rn. It's described by the null space of the matrix A, where A is an n by n matrix. Okay, and we may also consider projecting that. So what that means is in 2D case, is this x1, this is x2. That may be ax equals to b, may be this. But since this is 2D, so the ax equals to 0 is just a straight line passing through the origin, and we need to project some point. So I have a point here, we need to see how to project to that, or I have a point here, we need to know how to project it to the plane, to the straight line in this case, but it's a hyperplane in the general case. Okay, now let's consider a example. So suppose we have this constraint optimization problem where the objective function is a function of x and this quadratic function like that. The constraint is the x squared is equal to 1. Okay, so this is not a convex optimization problem. Remember that, because this one here, it doesn't give us a convex set, since this is just the sphere, right? It's just a surface of a ball, and that is not a convex set on the surface. It's not a convex set. Well, but we can still consider applying the projected gradient method to this minimization problem, to this optimization problem. So now let's assume that the Q is a non-negative, it's a positive definite matrix, and alpha we're going to use, suppose we're going to use this fixed step size. Then let's see what is the what this projected gradient method is doing. Okay, recall that the projected gradient method is to do this xk plus 1 equals to xk, projection of xk plus alpha dk. Okay, and let's say we choose this to be gradient. Then this will be negative gradient f of xk. So this is the f. This is equal to f of x. So the gradient f of x, we know that's just equal to qx. So this thing here is just negative qxk. So essentially, this is just taking the projection of xk minus alpha qxk. Okay, or we can combine the two terms. There will be projection of I minus alpha q times xk. All right, so that's what actually each step is doing. Now we know that we know what this projection will be because it's projecting to the sphere, and we know that we can just project in this case, unless this z is 0. But let's assume that we never reach to the origin. It's always a non-zero point, so we know that each projection just gives us this. Okay, so that means I'm just doing this one is just the inside divided by the norm of this inside itself. Okay, so that's what the projected gradient method is doing. Okay, and we're going to answer a few questions. First question, write down the explicit formula for this xk plus 1 in terms of okay. So we just did that. The second one is this possible to ensure convergence when alpha is sufficiently small? So suppose this is small enough, can we ensure convergence? The last one is that let's show if the alpha is between this and x0 is not orthogonal to the smallest eigenvector corresponding to the eigenvalue lambda mean, then the xk converges. Okay, so we're going to show that if alpha is in between and x0 is not orthogonal to the smallest eigenvector corresponding to lambda mean, then the xk will eventually converge to the minimizer. Okay, let's show this, all this stuff. So the first step is what we have computed. We know that the gradient is qx, the gradient descent gives us this, and the projected gradient is just that, right? So combining these things, we know that for each step, the xk plus 1 is just equal to this divided by its norm. And let's say the reciprocal of the norm is the beta k. So that's the beta k. So when we put this beta k back in here, we know that's what we set in the beginning. And then this is the formula for xk plus 1 in terms of xk. And now, let's say we try to let's say that x0 is an eigenvector of q corresponding to the eigenvalue lambda. Okay, if x0 is a eigenvector of q corresponding to the eigenvalue lambda, then what happens it happens that the x1 is equal to, according to our formula, will be equal to this. And because x0 is a eigenvector corresponding to the eigenvalue lambda, we know that this applied to x0 will be just x0 minus alpha lambda x0, okay, which will be this, right? That's because x0 is the eigenvector corresponding to eigenvalue lambda, right? That's because that I minus alpha q x naught is just equal to x naught minus alpha q x naught, and this is equal to x naught minus alpha q x naught, which is lambda x naught. So the x naught is the eigenvector. So I combine the coefficients, I'll just get that. Okay, and then we know this is just x0. Okay, so what have happened so far? We showed that the x1 is just equal to x0, so we didn't change. If x naught is an eigenvector corresponding to the eigenvalue lambda, then this always keep the same value. Okay, so actually the solution of the problem is an eigenvector, unit eigenvector corresponding to the minimum eigenvalue. And that's why if the x is not an eigenvector corresponding to, or x is so here, as we said, if x naught is not orthogonal to the smallest eigenvector corresponding to lambda star, what that means is if x0 is not spanned by the eigenvectors corresponding to the eigenvalues not equal to lambda mean, then we will show that this, starting from such kind of a point, we will never get convergence. But if we can find some point, if we start from x0 that has some component in the eigenvector corresponding to lambda mean, okay, it can be spanned by the eigenvectors, but one of the eigenvectors, and one of those eigenvectors is corresponding to the lambda mean. As long as it has such a one component or such part, then we can guarantee convergence. Okay, and at least what we saw so far is that if x naught happens to be just one of the eigenvectors, then we cannot really change the xk. The xk will stay the same. Okay, so now to be more specific, let's say that we sort the eigenvalues of q to in this way: the lambda 1 to lambda n. Lambda n is the largest, lambda 1 is the smallest, and they have the corresponding eigenvectors v1 through vn. Okay, and then this will span the whole space, as we know. Since q is positive definite, then all the eigenvalues are like that. The smallest one is greater than 0, and the corresponding eigenvectors will form a basis for Rn. And then let's say xk is said to be, let's say xk, since it's a vector, it can be spanned by these eigenvectors. Let's say that the coefficients for the span or for the linear combination is y1k through ynk. Okay, so these are the coefficients to assemble this xk. Okay, we don't know what is y so far. We will derive the formula for yk, but so far we know that since this is this y v1 through vn, this form a basis, we know that there must be some combination to form this xk. All right, now let's see. In this case, we recall that xk plus 1 is the projection of this point, and this point, according to our assumption right here, we can just substitute them back into this xk, and that will just give us, we know that will be just giving us beta k times the inside. So it will be the beta k times the I minus alpha q times this y1k v1 plus all the way to ynk vn. Okay, then we can apply this to each term, and the y is constant, so we can move it out, or can put it at the outside for each term, and then we just apply this to v1, and we know that when we do that, we will just get a 1 minus alpha lambda 1 times v1. That's what happens when we multiply this to v1, and that is this part. And as we said, we keep this outside, that's this. Okay, and we do this for all the terms, and eventually outside we have the beta, which is multiplied to each term as well. That's why each term, this is what the terms look like. Okay, so we have n terms like this. All right, now the beta k is the constant we got, or is 1 over the norm we got for the kth iteration. And let's say that we multiply all those beta together, we call this beta superscript k. So this is different from this beta k. This beta k is just so this beta k is just beta 1 times beta 2 all the way to beta k minus 1. Okay, and we know the meaning for these ones, so multiplied together is beta k. So this is for notation. We don't really know what the actual value is. It's just derive theoretically what will happen. All right, so now let's look at the in this case, what is yi k? So we know that the yi k, because I would say this one is supposed to be spanned by, so xk plus 1, according to our notation, should be y1k plus 1 v1 over the way to ynk plus 1 vn. Okay, and we know this too, and we also know that the xk plus 1 is equal to that. Okay, so that means this will be my y1k plus 1. And this will be my ynk plus 1. So it somehow shows us what's the relation between yk plus 1 and yk. Right? It shows us what is the relation between yk plus 1 and yk. So for example, the first one, if this is just equal to y1k plus 1, then let's say we reduce k by 1, then the y1k should be, just repeat this since this is 2 equal. So we know the y1k will be equal to beta k minus 1 times the y1k minus 1 times 1 minus alpha lambda 1. Right? That's just repeating the same thing, except that the k is reduced by 1. So the same thing here. We reduce the k by 1, we get that. Well, with this, we know that for each yi, we have the same thing similar. So if this is I, is also true. We just need to replace the corresponding I in that way. So the yik will be equal to that. That's exactly what this one is. Should be right here. And then let's see that for every time we reduce k by 1, we need to extract one more term like this, and then one more term like this. So you can imagine that when I keep reducing the k, eventually I will get the beta k minus 1. So if I keep doing that, it will be equal to the beta k minus 1, beta k minus 2, all the way to beta 1 times yi0 times 1 minus alpha lambda I to the power k. And then this, by notation, we know this is just a beta superscript k. Okay, so that's why we end up with that. So that shows the relation between the yk and the y0. For each component, it should be like that. Okay. Now, finally, we see that if xk is a linear combination of the vi's using the yk as the components, then this let's extract the y1k. So this is corresponding to this is like the coefficient for v1. That is corresponding to the eigenvalue lambda 1, which is the smallest eigenvalue. So extract this term, and all the other terms should be divided by y, right? So I just basically extract the y1k, and all the other terms should have yik divided by y1k. Okay, and then And then we can see that the ratio here, according to our derivation for the yi case, the yik is equal to that. So that's why I substituted back in here. The yik will be just equal to that. And the y1k is just the same thing, is that we have the y1 here. And now I have this ratio. And now this ratio, this will be cancelled, right? And then this y0, y10 will be kept here. And this, we can combine the ratio and then put the power outside, and then we have that. Okay, so now we know that the y1 naught is non-zero. The reason is the the x naught is equal to the y1 naught v1 all the way to yn naught vn. And since the x naught was assumed to not be a vector orthogonal to v1, so that means when we write the x naught as a linear span of the v1 vi's, this component cannot be 0. Okay, because if this is 0, then I know that my x naught will be perpendicular to v1, since all the other vectors are perpendicular to v1. So that's, in this case, x naught will be perpendicular to v1. That's not the case. We know that this must be, we know that this must be non-zero. Well, if it's non-zero, put it here, doesn't matter. It's always okay. Well, and in this case, we can see that this is non-zero, and everything is well defined. And if we choose this alpha to be small enough, by small we mean that it is between 0 and 1 over, this is the key, 1 over the largest eigenvalue of Q. So lambda is the largest eigenvalue. So in this case, this alpha is sufficiently small such that this quantity will be 1 minus alpha. So it's 1 minus alpha times lambda 1 over lambda. It's just this one here is just equal to 1 minus lambda 1 over lambda. It's smaller than that because my alpha is, this is bigger than 1 minus lambda 1 over lambda n, because alpha is smaller than 1 over lambda n. So 1 minus alpha lambda 1 will be bigger than this. Well, this is the smallest eigenvalue divided by largest eigenvalue. So I know this value will be smaller than 1, right? Smaller than 1. So that's why that the denominator is greater than 0. Similarly, this is also greater than 0. So the whole thing will be greater than 0. Moreover, since lambda I is bigger than lambda 1, so I'm subtracting this. This will be bigger than this. Okay, and that means I'm subtracting a bigger number from 1 compared to the denominator. So the numerator is smaller than the denominator, and that's why this is between 0 and 1. Since it's between 0 and 1, we know when take the power k, as k goes to infinity, this power just goes to 0. So that means this one goes to 0 as k goes to 0, and that means this one goes to 0. Okay, the yk goes 0. So remember, the yk is yk is a coefficient for the vi. So except for the first term, all the other terms goes to 0. Okay, all the terms, coefficient of the other terms goes to 0. Okay, and then we end up with just a 1 here. And since we end up with a unit vector every time, so we know that this term will just go to 1 because this is a unit vector. So I want, eventually, when all the other terms are gone, this divided normal of this is just the v1 itself. It's the unit vector, unit eigenvector v1. So that's why the xk will convert to v1. Okay. Well, let's look at a example, a more special example where the constraint is linear. As we said, we suppose we have this as our constraint, and we're trying to minimize fx such that this is true. Okay, so what this term let's see what this this problem is we're trying to minimize f of x subject to this this constraint ax equals to b. So if we do the projected gradient method, we need to make sure that every time we compute a new value, we need to project it back to the set of points which satisfy this. Okay, so my omega will be this set, and the question is how we do the projection here. Okay, how do we do the projection here? Okay, so we'll discuss the computation for this projection. So this part will be simple. It just depends on what the gradient is, but this part needs to compute the projection of any point back to this plane. But this plane, remember, it's still a hyperplane. It's just not look like it could be shifted away from 0. For example, the plane may look like this. Since it's not ax equal to 0, it's ax to b. So it's ax to b, so it could be something like that. And then we need to know that for any given point like that, how do we project it back to this plane, where this plane is ax equal to b.